So now let's investigate critical angle. What we want to see is how the relationship between the optical densities of the two media affects what the critical angle's value is. So how would you put that in a focus question? What is our independent variable? What is our dependent variable? Try yourself before I continue. We can say, how does relative optical density, in other words, N1 over N2, affect critical angle? What should we control in order to be able to answer this fairly? We must use the same color of light, the same wavelength of light for our different measurements. I'm going to choose red light of 450 nanometers wavelength. Now we need a table in which we can put our data. The question is, how does relative optical density, which in symbol form is N1 over N2, affect critical angle? So what will the heading of our table be, and what will the heading of each of the columns of our table be, and what are the units we're going to use? Table showing the relationship between relative optical density, in other words N1 over N2, and critical angle. We have two columns in our table. The first one's heading is about the independent variable, relative optical density. We could just write N1 over N2, or we could just write relative optical density. Here I'm actually saying the same thing twice. Notice there is no unit. This is unitless, so there's no brackets with a unit after that. And then critical angle does have a unit, it's degrees. So now, what are our relative optical densities? We don't know automatically. We know N1, we know N2, we can decide on those. So we need to add some columns to the left on this table. So we're going to have a place to write N1, place to write N2, and then we'll calculate N1 over N2. And then we're going to measure critical angle. So we open our simulation. Now we can decide what media we want. We will not get total internal reflection unless we have the more optically dense medium at the top. In other words, where the light is. If the light was at the bottom, we'd need the more optical dense medium at the bottom. But since the light is at the top, we need the optically denser medium at the top. So we are going to use the most dense medium possible in the simulation with an index of refraction of 1,6 at the top. And then for our first reading, let's use air at the bottom. So we put on the light, let's put on our angles, and now what we need to do is we need to find out what is the critical angle for this arrangement. And how do we do that? We change the angle of incidence. Okay, you see at this angle of incidence, 17,9, we are getting refraction and reflection. So this is not critical angle. This is smaller than the critical angle. So we increase the angle of incidence, and you can see that as we do so, the refracted ray is getting closer and closer to the boundary. And if we could get it, now I've gone over. If we could get the refracted ray exactly along the boundary at 90 degrees, then we would have the critical angle exactly. Now that's very difficult to do, so this is probably as close as we can get. 38,9 degrees. For our next treatment, we're still going to have the light going into air, but now let's have glass as our incident medium. So N1 is 1,5 and N2 is 1. And we can see that changing it like that has caused us no longer to be at the critical angle, because we are not getting total internal reflection, we're getting both reflection and refraction. So we need to increase the angle, and as we do so, we can see the refracted ray getting closer to the boundary, and we try to get at the minimum angle that causes total internal reflection, and we get 42,0 degrees. Notice if you do this, you might not get exactly the same angle, because as you can see, it's rather difficult to get the exact point at which you're getting the minimum angle that causes total internal reflection. So now we're going to use an incident medium having an index of refraction of 1,3, and you can see what we're doing is we're making the difference in refractive index between the two media less extreme. We're making the two more similar, and by doing so, we now need a bigger angle of incidence to be critical, because 42 was good enough before, but now it's not critical, as we can see by the fact that we're getting both refraction and reflection, not only reflection. So we have to increase the angle of incidence, and as we do so, notice how the refracted ray gets closer and closer to the surface. If we could get it exactly at 90 degrees, They have overshot. If we could get the angle of refraction to be 90 degrees, that would be exactly the point where we have our angle of incidence equal to critical angle. That is very difficult to do. As you can see, it changes very quickly from refracting to total internal reflection. So we hope that's the minimum incident angle that causes total internal reflection, which is another way to define critical angle, 50,4 degrees. Now I'm going to put medium 1 as glass and medium 2 having a refractive index of 1,3. And we can see that 50,4 degrees is not the critical angle. We're getting both refraction and reflection. We need to increase the angle. As we do so, the angle of refraction nears 90. If we can get it exactly at 90, we're nearly there. Perhaps that's right. At the instant that we get total internal reflection, the minimum angle for which we get total internal reflection, we can take that as being the critical angle, 60,2 degrees. And then we're going to put our medium 1 as having a refractive index of 1,6 and medium 2's refractive index 1,5. So medium 2 is glass. And so we can see that the two media have quite similar refractive indexes. 1,6, 1,5, very similar. And as a result, we need to make the angle of incidence quite large before we reach the critical angle. There we have angle of refraction 87,1. So it's nearly 90, so we're nearly there. But we need to make it a little bit bigger. And maybe that might be it, 71,3 degrees. It is difficult to be accurate here, so if you repeat this experiment, you will probably get somewhat different results for the critical angle, but you will get the same trend. So this is the data that we've collected. Now what we need to do is to calculate N1 over N2 for each of these situations. And this is what you should have found. So our question is, how does relative optical density, in other words the ratio between the optical density of medium 1 and medium 2, affect critical angle? So what is the answer to this question? Drawing a graph might help us to see the answer. You need to supply the labels that are missing. Pause until you've done this. So we have relative optical density, in other words N1 over N2 on the x-axis, and critical angle in degrees on the y-axis. This is a graph showing the effect of relative optical density on critical angle. And so how do we answer this question? Our conclusion is, the greater the optical density of the incident medium relative to the refractive medium, in other words, the greater the difference between the optical densities of the two media, the smaller the critical angle. So the more optically dense the incident medium is than the refracted medium, the smaller the critical angle, the easier it is to get total internal reflection. And this is used in a number of applications, one of them being diamonds. Diamonds are cut in such a manner that you get a lot of total internal reflection happening within the diamond. Diamond is a very optically dense medium. So when light enters diamond and then travels from inside the diamond towards the outside, it is moving from an optically denser medium, the diamond, into an optically less dense medium, air. And because there's a very big difference in optical density between diamond and air, the critical angle for the diamond-air interface is very small. So it's very easy to reach the critical angle. It's very easy for total internal reflection to happen. So total internal reflection happens inside the diamond over and over and over as the light bounces around inside the diamond. And then eventually it will strike a side of the diamond at an angle greater than critical and emerge from the diamond. And because the light has been bounced around a lot inside the diamond before it reaches that point, the diamond sparkles because the light comes to your eye from many different angles where it eventually can exit the diamond after being bounced around inside. And diamond cutters cut the angles of those faces such as to increase the chance that the light bouncing around will strike at an angle greater than critical. In other words, will carry on being bounced around and therefore sparkle even more.